every electric current produces a magnetic field. And depending on the shape of the wire, you will have a specific shape in terms of the magnetic field. Now, a single straight wire which carries a direct current, well, this type of wire is going to be surrounded by a circular magnetic field, and this is illustrated in the diagram. Now, what is very important is that if we were to take any point on this wire, then at any particular point on that wire, we can say that the magnetic field strength is going to be the same at any point on that wire. And the magnetic field strength is going to be made up of concentric circles representing the magnetic field. So it doesn't matter where you are on this wire, the magnetic field strength or the magnetic field will be the same at every particular point on that wire. Now, you can in fact produce a much stronger magnetic field from a straight line wire, and this is done by twisting the wire into a very tight coil, and this tight coil is usually called a solenoid. And this solenoid creates a magnetic field which is very similar to that of a bar magnet. Now, the magnetic field which is caused by a current can be illustrated using the wire that we've just mentioned, a straight line wire. So let's consider a current carrying wire as illustrated in the diagram on the right hand side. Now, here you can see that there is a current flowing from top to bottom as represented by the red arrow in the diagram, and we're going to represent the current flowing through that wire by the letter I. Now, if we were to place a compass around the wire, then what we would find is the following. We would see that a magnetic field is produced, and that this magnetic field is in fact tangent to a circle surrounding the wire. And here we can see this illustrated in the diagram. In this case, the wire is moving in this direction into the page on the right hand side and out of the page on the left hand side. And again, we can see that we have another layer of magnetic field lines, and we can see the same at this position here. Now, this particular phenomenon is quite an interesting one. The magnetic field lines do not originate on the wire. So the magnetic field lines are not on the wire. They're actually encircling the wire. And the other important phenomenon is that these magnetic field lines, they have no beginning and they have no end. The other important phenomenon is that if we were to reverse the direction of the current, in other words, if the current, instead of moving through the wire from top to bottom, let's change it so that the current is moving from the bottom to the top, the magnetic field lines will also be reversed in terms of their direction. You grip a wire so that your thumb points in the direction of the conventional current, and that's from the positive to the negative terminal of the battery. And then once you've done that, you curl your fingers around the wire, and your fingers will be in the direction of the magnetic field. In other words, your fingers represent the flow of the magnetic field from the north to the South Pole. And so the right hand grip rule gives you the direction of the magnetic field around a straight wire. We've seen the use of the right hand grip rule in terms of identifying the direction of the magnetic field as a current flows through a straight wire. Now we can use the right-hand rule in a similar way with a solenoid. And we can use the rule to find the orientation of the magnetic field around a solenoid. Now, if we look at the diagram to the right, you should be able to see a solenoid. And a solenoid really is just a wire, a straight wire, which has been curled around in such a way that it's produced this coiled effect with the wire. Grip the solenoid so that your fingers now follow the direction of the conventional current. Now, this is slightly different to the application of the right-hand rule that we saw earlier, because when it came to the straight wire, the fingers represented the direction of the magnetic field. But in the case of the solenoid, your fingers would represent the direction of the conventional current. In other words, the direction that the current is flowing from the positive to the negative. So your thumb now, that will point towards the north pole of this electromagnet. So by passing a current through this coiled solenoid, you're actually generating an electromagnet. And that electromagnet is going to generate a magnetic field, and that magnetic field is going to be in the direction of your thumb. So the electromagnet can be made stronger by increasing the number of coils, or alternatively, you can add an iron coil in the middle of the coils which are curled around. So again, continuing with our theme of looking at the magnetic field direction of a solenoid, we can see that in the diagram here that a solenoid is really just a series of loops which are stretched out as shown on the right hand side of this slide. And as we saw earlier on in the previous slide, there is a right hand rule for solenoids. So again, just to recap, with your right hand, you grasp the solenoid in such a way that your fingers curl around it in the direction of the current carrying loops. So here you can see in the diagram that the current is flowing in the direction of the arrows, and the fingers are actually pointing in the direction of the arrows, indicating the flow of the current. And then your extended thumb then points in the direction of the north magnetic pole. So we need to ask ourselves the question, what does the magnetic field look like around a solenoid? But if you look at the diagram here on the left hand side of the slide, you can actually see what those fields look like. And they look very similar to the magnetic field generated around a bar magnet. So we can illustrate the magnetic field flow through the solenoid as in this animation illustration here. So you can see that these represent the coils which form part of the solenoid, and you can see the magnetic field intensity inside of the solenoid, and as they come out from the solenoid you can see their distribution around the solenoid. Now in terms of an actual picture of what this might look like in reality, here you can see a diagram of a solenoid in which you have the wire, the coiled wire, which is wrapped around, and here you can see an iron core which is inserted inside the solenoid in order to increase the magnetic field strength generated by the solenoid. Now you can in fact do an experiment to investigate electromagnets. If you have a core of iron inserted inside the solenoid, that will increase the strength of the electromagnet formed. If you don't have an iron core inserted in between the solenoid, then that solenoid won't become an electromagnet and its magnetic field strength won't be as large as it would be if you had a core of iron inserted into the coil. So you can carry out two experiments to investigate a number of factors that can affect the strength of an electromagnet. And you can in fact investigate how the number of coils affect the number of drawing pins which are attracted to an electromagnet. And here you can see that we have an electromagnet which has been formed by wrapping this coil around a core of iron, in this case a nail. And what we're going to do is to pass a current through this coil of wire and generate a magnetic field, and we're going to see just exactly how many drawing pins can be attracted to this electromagnet, and that's dependent on the number of coils of wire. So if we increase the coil of wire, does that have an effect on the magnetic field generated by the electromagnet? And we're going to see that by doing this experiment, whereby we change the number of coils and we see how many of these drawing pins will be attracted to the electromagnet. And we will keep the current the same while we do this experiment. Now, we can also do another experiment where we vary the size of the current flowing through the solenoid, and we can see how many drawing pins are actually picked up when you vary the current flowing through this solenoid when you have a core of iron inserted into the coils. So we're going to have a look at those experiments now. So let's begin by asking the question, what do we mean by the term electric motors? And an electric motor is in fact a device that converts electrical energy into mechanical energy in order to produce a turning effect. Now, most motors, they are powered using what we call direct current, which is DC. These direct currents, these are produced usually by cells and batteries. Now, there are some motors which are powered by mains electricity. And if you have a motor which is powered in this way, then that motor is going to be using what's called alternating current. In other words, AC current. Now, these motors tend to use electromagnets rather than permanent magnets. So now let's just have a look at how a simple DC motor works. And in this animation, we're going to explore the principles behind the working of a DC motor. So in the diagram, we have a horseshoe type magnet. And you probably notice that in between the north and the south pole, what we have is a wire which seems to be bent into this particular shape. And one end goes in this way in terms of the green wire, or the green part of the wire. And then when we come to this part, which is the orange part of the wire, you can see that it comes out, and both of these parts, the green part and the orange part, they actually touch these two brackets. And we're going to explore in detail exactly what is happening in this diagram in relation to these two brackets. So an electric motor uses the turning effect of a current carrying coil in a magnetic field to produce rotation. So let's click on the labels to find out more about the main parts of this motor. The coil of the wire which is used in this motor is insulated and is actually free to rotate on the pivot. Now, what that basically means is that this wire is coated with a insulating plastic type material, and it's allowed to move very freely without any hindrance as it rotates in the middle of these two poles of the magnet. Now, these devices here, which I called brackets, well, they do have a special name, and they are in fact called commuters, or a commuter, if you think about just one of them. So a commuter is a split ring commuter, and the split ring commuter is sometimes just called a commuter, and it's attached to the coil and it rotates with it. It connects the coil to the power source. So in other words, this particular commuter actually is in contact with this particular strand of the wire. When this wire rotates, as it will do in the middle of this magnet, then this particular part will actually brush against the commuter as it rotates. And we'll explore exactly what happens when we look at the workings of this DC motor in more detail. Now, this part of the motor is called the brushes, and the brushes, they tend to be graphite brushes, and they rub against the commuter and they connect the brushes to the power source, and the power source is actually responsible for allowing the rotation of the coil of the wire. Let's have a look and explore what happens when we turn on the switch. So when the switch is closed, the current flows in an anti-clockwise direction through the coil. And this creates opposing forces that makes the coil rotate clockwise. So in other words, when we turn on the switch, this coil will start rotating anti-clockwise. And as it rotates anti-clockwise, this creates an opposing force that makes the coil then rotate in a clockwise manner. Now, when the coil is in the vertical position, the commuter is no longer in contact with the brushes. So you can see that here. This is the actual commuter, and you can see that because it's actually rotating, because it's connected to the coil, and as it rotates, there comes a time when it's not actually in contact with the brushes. And you can see here that the metal part of these commuters are no longer in contact with the brushes. So at that point, no current will be flowing through the system, through the coil. And so there won't be any forces acting on these coils. However, what happens is the momentum of the coil actually pushes the actual coil past the vertical. And when it does that, the commuters now touch the brush again. So you can see here that this commuter is now touching that brush because of the momentum of the coil pushing it forward so it touches the brush. And when that happens, the current starts to flow through the coil, but this time it flows in the opposite direction. And we can see that the reversal of the current through the commuter and the coil means that the force acting on either side of the coil is also reversed. And you can see that here in terms of the red arrow. And so this makes the coil continue to rotate in a clockwise manner. So as the coil rotates another half turn, then the commuter reverses the connection and the current again. And this means that the forces acting on the coil, they are also going to be reversed. The principle of the electric motor can be illustrated very nicely in the animation shown. So before we look at the Faraday's experiment, and also before we go into details to see the relevance of the experiment, we need to know what is electromagnetic induction. Now, in order to understand electromagnetic induction, you need to recap the relationship between current and magnetism. And in order to do that, let's just have a look at a few points. We know that all currents have a magnetic field associated with them. In other words, if you were to allow current to flow through a wire, then that wire would generate a magnetic field around it. We also know that a wire which is put in a changing magnetic field will experience an induced current. Now, this is probably one that you've probably not come across. And this is the one that we're going to be looking at in some detail as we study electromagnetic induction. If you have a magnetic field which is changing, that means the magnetic field is changing in terms of its intensity, or the magnetic field is moving in some way, then if you place a wire in that moving or changing magnetic field, what will happen is that a current will flow through the wire. So in other words, the wire before will not have any current flowing through it, but once you place it in a magnetic field which is changing, then you will see current flowing through the wire. So going back to the first point, all currents have a magnetic field associated with them. This is the basis of what we call electromagnets. And the second fact that a wire in a changing magnetic field will experience an induced current, well, this effect is called electromagnetic induction. Now, in this animation, we're going to explore the movement between, for example, a magnetic field and a coil. And remember, in this circuit, there are no batteries or there's nothing generating electricity. It's just a wire connected up to an ammeter, which is going to measure the amount of current flowing through the wire. So let's move this magnet, and then as we move it, have a look at the ammeter and see what happens. Keep your eyes on the ammeter and then just observe what happens when we move the magnet through the coil. Right, you should have seen that the needle on the ammeter actually moves in this direction to the positive, and then when the magnet stopped moving, it then went back to zero. So there was a movement from zero to a positive value and back to zero when we moved the magnet into the coiled wire. So let's just summarize that. When the magnet moves, a current is induced in the coil. In other words, a current is produced in the coil, and then when the magnet stopped, then so did the current. So there was no current induced in the coil. And we're going to move it out of that coil, and we're going to move it back to its original position. Right, what you probably noticed was that the needle on the ammeter actually flipped to the left-hand side. So let's just summarize that. As the magnet moves out of the coil, a current is again induced, but it's induced in the opposite direction. And that's the reason why the needle moved from this position to the negative position when it was moving out of the coil back to its original position. But remember, when we took the magnet from its original position and moved it into the coil, then you saw the needle move to the positive section of the ammeter. So going back to our explanation, what we can say is that in order for power to be transferred continuously between the two circuits, the current in the first circuit must be changing continuously, and this can be achieved by using an alternating current. And we also saw that in order for as much power to be transferred as possible, the two circuits must be as closely magnetically linked as possible. And how do we do that? Well, this can be achieved by winding the two circuits into a tight coil around an iron core, and this is called a transformer. And this is the basis of what we call a transformer. It allows current to be induced in a set of wires from another set of wires in which a current was flowing through, because the current flowing through the first set of wires induces a magnetic field, creates a magnetic field, and that magnetic field induces a voltage in the second set of wires, which then causes current to flow through. So now let's have a look at some of the properties of transformers. Well, essentially transformers, they transfer power between circuits which are not touching each other. And the design of a transformer actually determines the characteristics of the nature of the electricity which flows into the secondary circuit. Now, the frequency of the alternating current in the secondary circuit, that will always match the primary circuit. But what about the current and the voltage? So we know the frequency will be the same, but will the current and will the voltage be the same? Well, I guess the answer to that is no, because we know that the purpose of a transformer is to basically transfer power between circuits. And we could have on the left-hand side, the primary side, that the voltage may be higher or it may be lower than on the secondary side. So the voltage in each circuit is related to the number of coils on each side of a transformer. And it's related by the following equation. The primary voltage, which is the voltage generated on the left-hand side of the transformer, divided by the secondary voltage, which is the voltage induced in the right-hand side of the transformer, is equal to the number of turns on the primary side, or the primary turns, divided by the number of turns on the secondary side, or we can call these the secondary turns. So this is a very important expression in terms of being able to determine voltage on either the primary or the secondary side, or the number of turns on the primary or the secondary side, if we know either the voltage or we know the number of turns. So there are two types of transformers. There's a step-up transformer and there's a step-down transformer. Now, a step-up transformer is used to increase voltage, and this tends to have more turns on its secondary side than it does on the primary side. Now, the power in the secondary circuit cannot be greater than the power in the primary circuit. If this was the case, then the transformer would be more than 100% efficient. You can't have more power on one side than you have on the other side because of conservation of energy. Now, what is the relationship between power, voltage, and current in a transformer? Well, the power is equal to the voltage multiplied by the current. So if we know the power, we can determine the voltage, but more commonly, if we know the voltage and we know the current flowing through one side of the transformer, we can then determine the power in that circuit. So in a step-up transformer, there is an increase in voltage. So in other words, we can step up the voltage in this side, but as a result of that, we end up reducing the current. Why? Because of this equation here. So you can't have more, for example, voltage and current in one side than you have on the other, because the power is the same on both sides. The power in the secondary circuit cannot be greater than the power in the primary circuit. So what does that mean? Well, let's have a look at some examples. A transformer has 100 turns on its primary coil. It has an input voltage of 35 volts and it has an output voltage of 175 volts. How many turns are there on the secondary coil? So let's just go through this one together. We would use the expression that the voltage in the primary side divided by the voltage in the secondary side is equal to the number of coils on the primary side divided by the number of coils on the secondary side. So if we substitute what we have in terms of the expression, what we can do is we can actually rearrange this expression in this way. And that's quite legitimate to do. We just rearrange everything. So we have voltage on the secondary divided by voltage on the primary is equal to the number of turns on the secondary divided by the number of turns on the primary. And again, we can even rearrange this expression in the following way. We can say that the number of turns on the secondary divided by the number of turns on the primary is equal to the voltage on the secondary divided by the voltage on the primary. So all we've done really is just to rearrange the expression for the equation relating voltage to the number of turns. So in this case, we can determine the number of turns on the secondary side of the transformer, and it's just going to be equal to the voltage on the secondary side of the transformer divided by the voltage on the primary side of the transformer multiplied by the number of turns on the primary side. And so substituting the values that we have, we know that the voltage on the secondary side of the transformer, which is the output voltage, is 175 volts. And we know that the input voltage, which is the voltage on the primary side, that's 35 volts. And we know the number of turns on the primary side, that's 100 turns. So if we multiply this value by 100, what we get is an answer of 500 turns.